Now I've chosen this exercise from the latest NSC, the National Senior Certificate Physics exam. We have a building. Does that remind you what we've been doing? Now a ball is thrown upwards at 8 meters per second, and then it falls down, and after 4 seconds, it hits a balcony. Then it bounces upwards, and after a further 6 seconds, the problem explains, it then hits the ground. You've got to calculate at what velocity it hits the balcony with. Right, then getting on. They ask us to sketch a velocity time graph for this whole problem. So let's do that. I've set up the axes of the graph. Okay, at time is 0, what is its velocity? The time equals 0, so we've got time in seconds, we've got a velocity time graph, that's our heading. We've got velocity in meters per second. I've got a range that is both positive and negative, because don't forget our ball starts going up and then its velocity goes down. So, look at this. At the starting time, t equals 0, it's going up at 8 meters per second. So there is our starting velocity. And we worked out that after 4 seconds, it had a velocity of minus 31,2. So after 4 seconds, it was minus 31,2. So there we go. So is our graph just a straight line? Is the velocity changing constantly like this? I'll just draw the graph. And actually it is. Let me tell you why. You can work it out for yourself. It starts at 8 meters per second, and we know that every second it loses 10 or 9,8. So after time equals 1 second, it's going to have a velocity of 8 minus 10 of approximately minus 2. After 1 second, it's going to be minus 2. After 2 seconds, it's going to have added 10 to it, or 9,8 to minus 2. It's going to be minus 12. There we can see, minus 12. And every second it adds 9,8, or approximately 10. So this is in fact how our graph looks. So far, easy enough. Then they explain how the ball, when it hits the balcony at 4 seconds, bounces upwards at 27,13. Now that's an upward velocity, a positive velocity of 27,13. And that happens after 4 seconds. So at 4 seconds, it acquires 27,13. So there's 20, 30. It's a positive or upward velocity of 27,13. So here is where it hit the balcony, then it bounced up, and then it continued to fall. And after 10 seconds, my graph only goes to 6. After 10 seconds, it hits the ground. So from here, how would I continue my graph? Well, I know that from there, every second, it's going to lose 9,8. So if I wanted to draw this accurately, what I would do is, here we've got a velocity of 27, 0.13, but after 1 second it will have lost minus 9.8 equals, it'll be 17.33. So if I wanted to draw it accurately, it would be 17.33 at 5 seconds. (17.33), and take a guess how much will be less after another second. Well, again, 17.33 minus 9.8 gives us 7.53 after another second. So at 6 seconds it'll be 7.53. At 6 seconds it'll be 7.53. And so on. So, what you end up with is the following graph, and this is what they're looking for. That this should be parallel to this, because both times it's falling at 9.8 meters per second, so it's changing by a constant amount every second. So its velocity is decreasing by the same amount whether it's going up or after it's bounced. Now the only thing of interest here is what happens during the bounce. Now what they in the memo give is a dashed line, meaning they give up trying to figure out what happened during the bounce, which I guess is fine for us in matric. We don't know. But we know that when a ball bounces, let me get a ball. Here's a ball. When a ball bounces, there's a period of time when it comes to a stop, then it reverses direction. And it takes a finite period of time for a ball to bounce. So for a period of time, its velocity is whatever it was coming with, then it hits the desk, then it bounces back with its velocity. So we know that it hit the balcony at 31.2 meters per second, and it bounced back up at 27. So 31 to 27, it lost approximately 4 meters per second in the bounce. And I thought, just as a matter of interest, just for the sake of interest, you folks might be interested in seeing this. Can we work out the bounce? Now, what I have here is a little Acer notepad, and it's got Audacity sound audio editor on here, and what it does is it'll show the waveform when a ball bounces. So what I'm going to do is go to start recording, and then I'm going to drop the ball. Okay. Now I'm going to stop it. And I don't know if you can see that waveform. But look, there is the bounce. As it hit, and it bounced 3 times, 1, 2, 3. As it hit, that little blue squiggle there represents the period of time that it was bouncing for. And what I'm going to do is I'm just going to zoom in on it. So they've got a zoom tool, and here it is. And I'm going to go here. And there you can see is the zoomed in sound that it made. So here is where the actual bounce occurred, and when you look at it, 0.95 is there, and there's 1, and there's 1.05. So this is between 9.5 and 1.05. So the squiggle lines go from 0.975 minus about 1.03. 1.03, and my calculation shows me it was 55 milliseconds that the bounce lasted. 55 milliseconds. So that means 55 thousandths of a second that this ball happened to be in contact with the desk. I thought that would be just interesting for you if you want to work out how long a bounce actually lasts.